Okay, good. Ooh, another echoing day, you know. Okay, so still echoing, that's good, you know, cheer me up. So I think, you know, we started studying about turning, and then, you know, today we want to go a little bit, you know, in depth, which means terminology, and then how we are going to understand the process. Because from now on, I will use, you know, like machining terminology a lot. And you probably did for like turning, like last time I said lake, flank, or, you know, what else you studied, you know, terminology-wise, you know. But I think we can review. And then also drilling and milling. These are kind of a major process. After that, we will do like maybe broaching, and then that's it. It depends on the time, you know. And so anyway, today let's go, you know, terminology. So that's, you know, figure 7.3. So I'm going to, you know, write today is November. Sadly. So that's figure 7.3. Don't you think time flies? Right? My October is like gone. You know, I don't know if you remember, I had 3 trips. You know, trips, if somebody takes care of my job, I don't mind going somewhere, right? 3 trips, job is there, right? So multitask, then crunching, right? So, you know, because I don't want to waste this time, you know, your meeting with you is my luxury. This is a great time, you know, right? So I don't want to miss it, and I really, you know, I want to enjoy, you know. So, but time flies. Whew, I have to catch up, so let's go, you know. So figure 7.3, so look at this screen, you know, first. So this is a turning, right? This is a workpiece. Right? And then you have, you know, this cutter, you know, tool bit. And then in this case, you rotate this direction, right, coming to you. And then you know, move your tool from right to left. Because this is right hand race, right? You know there's a left hand race too, right? So depends on how you move, you know, your tool. And then right hand and left hand. I believe you use right hand, right? Right hand race, right? Yeah. So that's, yeah, here. And then if you think about this, you know, like this one, this is kind of what's happening here. You know, the kind of side, different view. So this one. So let's focus this side. So let's draw together. You know, I'm old-fashioned, but I think if you draw together, that's good. And then now what? I need that. I can try, but trying doesn't help. Okay, so tool, right? And then this is kind of, you know, orthogonal cutting. Have you ever heard of orthogonal cutting? Orthogonal, like 90 degree, right? Orthogonal. So then I draw, I said this, you know, view, like, you know, figure 7.3. So that's kind of what's happening here. Like this is lace, it's 3-dimensional. So orthogonal. So in this case, if you think about, forget about this one. So, you know, now this is a 2D, think about this 2D, right? And then if your workpiece, you know, like width is perpendicular to this, you know, page. And then you can think, this is a tool, this is workpiece, and then like that, oh, sorry, let's go, like that, right? Chip create like this, right? So that's, so your cutter, and then this is, you know, like you move this way, and then cutter is like this 90 degree, you know, perpendicular, you know, to, you know, this, and then chip goes this way. That's the orthogonal cutting, you know. So that's a very fundamental, you know, case. So that's actually, you know, similar to that. So lace is 3-dimensional, right? Lace is 3-dimensional, but we can think, you know, that process as a 2D. So that's what I am drawing, you know. So anyway, this is a chip. Okay, so this is your work, right? And then this is the tool, and then this is a chip. Creating a chip is the key. You have to create a chip. You have to pass your heat to chip. So generally 60 to 80%. Because unless you pass the heat to chip, okay, conservation of energy. The heat has to go somewhere, right? And then if you hold the heat in the workpiece swollen, right? Because usually thermal expansion. And then you cut. Usually you overcut, because after that it shrink. If you keep heat in tool gets like maybe a little bit softened, okay, but it's relatively speaking, it's not softened. Usually it creates some chemical reaction against the tool surface because the temperature is not like 30, 40 degrees. Temperature is like what? About 700, 800 degrees Celsius, right? And then you are cutting, separating material. So then you will have some chemical reaction, oxidation. That's going to cause tool wear. So chip, super important. And then we have to say really nicely buy. You don't want to keep it. So then terminology we said. So first, this, you always have angle, right? You always, when you cut. But actually you have 90 degree, 0 degree, or even negative. You can have it. But this angle, we usually use alpha. This is rake angle. Because to this surface, actually chip goes, that's rake face. That's why we say rake angle. Okay? So then this rake angle, this positive, this negative. So like 5 degree, 15 degree, like I just show, right? So, right, let's go this way, right? Your shaver too. So this is cutter, right? Usually you go this way, right? Little bit angle, right? And you don't do this way, right? You can, but go like that, right? Because you are going to keep this cutter sharper, then chip flow like that, So that's why we call this positive. Usually like 5, 10, maybe 15 degree you can do, because even if you go like that, it's gonna maybe chip, right? Be too sharp, right? So then if you go like 90 degree, which is like perpendicular, right? So you can do, this is workpiece. You can do this, right? But then maybe compared to that, performance may be not as good as the case with this. Go like that, you can cut too. But again, chip goes like bend like that, right? So maybe that's not so good. But why we have this case? There's a reason, right? Why you are sitting here? Reason, right? Everything has a reason. Otherwise, it disappears, right? So then why? Because if it go like that, I said it's going to chip. So then if you go like this, maybe much, rigid, tougher, and then go even tougher. So if you use metal or tungsten carbide, I don't know what kind of tool you use, usually go this way. But if you use ceramics tool, diamond tool, then that's hard, right? But it's fragile. It's going to chip quickly. That's why to make this diamond or ceramics tool give toughness. Material you cannot change, but how you contact, right? Make this tool contact against workpiece. So that's why go like this or that. And you can just kind of support, or prevent from chipping. So abrasive is always negative. It's like a lock, right? So lock case, always. So this is abrasive, because abrasive is like a lock, right? And then if you have workpiece, so this, in this case, this is depth of cut, right? Abrasive is tiny, right? Tiny depth of cut. So you don't even know like that. It's very tiny, and then chip created like that. So yes, you have tiny, tiny depth of cut. Let's put the depth of cut. So in this case, rake, super negative, So then abrasive, diamond abrasive, other abrasive, ceramics, usually ceramics, right? Alumina, What kind of abrasive you know? Aluminum oxide, right? So Al2O3, right? Alumina and then silicon carbide, right? Like if you use sandpaper. Did you use sandpaper? Right, right? Even you don't do any machining, but like if you do plastic model, like I do Gundam. I'm making Gundam. Yes, I do. Awesome, right? I spent just $100 last week, So, why? I do, collection. What's wrong, If I can show you if you come to my house, it's collection, right? But yeah, but it's so fragile, because $100 like this size, If I spend only $30 like this size, right? Yeah, I can go like any Gundam, right? But even Gundam or plastic model, I have to go back to the sandpaper, Sometimes I have to do, right? Because the cutter, recent cutter is very nice. Even if you spend maybe like less than $20, even $10, the cutter is so sharp. But still some bar, right? You have to do a little bit, So something like that. But back to the sandpaper, right? Use like diamond or abrasive is there, right? Usually you don't see the diamond sandpaper. It's very expensive. But backside, you see A and sharp, let's say 100, C sharp 100. You see it. So this A, that's aluminum oxide. C is silicon carbide. And then if you see this number, that's mesh, right? So then how small, how big the abrasive is. If your number is larger, then abrasive smaller. What size of sandpaper did you use? You don't pay attention? 30-50? Yeah, that's kind of a rough side. So if you use sandpaper for the US, if you use like imperial, because there are two units, imperial or English unit, base or metric, right? So then this mesh means 1 centimeter. So like 1 centimeter equal 10 millimeter, right? 10 millimeter. So then in 100 case, sheathing, how many like wire? So that means you have 100. And then if you go like mesh, like 30, like she said, so which means 1 centimeter, you have only 30. 30, right? So that's why if you go higher, increase mesh number, means you have a smaller, finer abrasive. So this is the matrix. But how about for the imperial case? Then you will see sometimes, like because it depends on where, what manufacturer, what company, where you buy. That's 1 centimeter is going to 1 inch. Right? So even if you buy same abrasive paper, same 100, but depends on what their like manufacturer use, what means like a standard, then 2.54 times difference. So when you buy abrasive, I don't think you will have you will buy abrasive in the bucket, but probably you may have opportunity for sandpaper. So make sure what you want. I'm just telling you because I made a mistake. I came to US for, I think I talked a little bit, right? My career, right? University and industry and the national lab, I did everything, right? So I came to industry. I have never worked for industry in Japan, only the US. So then from Japan to US, right? I had only Japanese standard, right? And I ordered abrasive. Oh my goodness. It's based on the like imperial, like American unit, right? And my imagination, and I opened the bucket. Oops. And then company-wide, I don't buy just one bag, right? Bucket, right? Because I was doing that time like wheel, like a car wheel. Yeah, that's kind of, I'm an abrasive person, but like, polishing. Wheel, especially for truck. I don't know if what kind of wheel, you don't have to be like, car mania, but, just when, you see the wheel, I know I have to talk about cutting, but wheel Oh, I cannot draw. Right? Let's say wheel has some kind of, air. Then you have a tire, rubber side, right? This is rubber side, right? This air, the shape is super important. Airflow, how you tire like rotate, right? How air goes. So super important, especially this surface, like inside, it's a really good curvature. It's there. And then if it's coming to truck, trailer, or trailer is big, right? How many tons you are talking about? Like your car, probably a little bit over 1 ton, right? Do you have a sense of the mass of a car? Your car should be a little bit over 1 ton. Okay, it's not like a kilogram order. Tiny miniature should be 1 ton. And then, how many parts you have in your car? I hope you have a sense, you are mechanical engineering, or aerospace to, measure, right? But back to here. So super important, because otherwise vibrate, right? It's gonna crack. Then tire is very, tire play super important role, right? When you drive, so then sometimes, really damage people. But anyway, back to, my career is fine, but what is this role, Come on. Okay. Then abrasive, so just, I made a mistake and I have to reorder. That's why I will never forget. So I just want to share with you, don't make same mistake as I did. So this is, rake angle. Oops, rake angle spends so much time. Let's speed up. Where's my note? Yeah, so then another important angle-wise, so that's shear plane angle. So this angle. Usually we use phi. So this, some people may say shear angle, but shear plane angle. Because this plane, that's a shear plane. If you have like really nice curly chip, shear plane angle should be larger. If you have a lot of friction, shear plane angle is going to go smaller. Chip is going to be fat. It's very difficult to push. So that's another important part. And then this, another angle. So this is, okay, maybe gamma, and then relief angle. Then this face, that's flank. Flank face is the face we check tool wear. So we check flank and then how much we just damage. So if you have no relief angle, so like sliding on the surface, then you will damage, right? You are actually accelerating the like tool wear. So that's why we have to have a slight relief angle. If you remember the drawing and the extrusion, the end of the like die, we put the relief angle, right? Same role. We have to give them some relief, Then we can have like longer tool life. Tool, how much you spend to buy, tool, right? The tungsten carbide. Once we go, I will explain my research a little bit, the cutting, because I love cutting. And then one piece, $20, it's bare. $20, and then if you spend this $20 every 5-10 minutes, how much you're going to waste your money? When you have to change tool, you have to stop machine. That's another waste. And then once you stop machine, you change tool, you have to recalibrate with 0 something like that, right? Checking how many minutes you waste. Right? You cannot do that. That's why tool wear is important, and I think Dr. Schuler gave some sort of lecture about the tool material. So anyway, flank, we will come back, when time comes to study about tool wear, So I want you to remember that. So anyway, this one is, the kind of terminology for turning, and then also orthogonal cutting. That this is a very fundamental. Any questions? Good. And then next, 7.2.3, machine tool. right? Because we are talking about the turning. So lathe is the one, one like which means machine tool you are, using, right? So then I think we have, some picture. This is older picture. So then that's, 712. Okay. 712, And then I'm just going to leave 713, 714, yes. Okay. So then this is a huge race, right? And I don't think, oh, that's my drawing, but, so this, you operate, this is too big, I don't know, DML or others, probably you operate manual machine tool, right? Not like CNC, right? I mean, right, for the beginner, right? So then, this is a chuck, and then tool post, right? And then, you put the workpiece here. So 713 shows a little bit, like more kind of, instructional or more, maybe instructional figures, So that's, like x-axis and z-axis. I want you to remember that, because sometimes we always say x is like that, right? The race, x is go like that, And this is like a top view, top view. And then workpiece is, workpiece and chuck, right? And then tail stock coming from right side. I mean, I hope you remember. This is, refreshing your mind, like tail stock, right? Because sometimes, or a lot of cases, you use only chuck, right? So you chuck, you use dial indicator to make sure your workpiece is like correctly chuck, right? Otherwise, the workpiece is going to be like run out or something like that, right? So you put the dial indicator to rotate workpiece, and then do you know dial indicator? Good, right? Otherwise, what am I talking, right? Like that, and then needle goes and like that, and then you can machine, right? So that's workpiece, and then, this is the carriage of the lace, right? And then tool post is here, you rotate, and then apron, and then saddle, So these are like, the very simple one. So when you operate race, first, I want to always check is stop button, right? How to stop the machine, like red one. But sometimes you don't see it. It's a small one. How to stop the machine if you don't have any, like emergency stop button? Or you don't use that kind of manual small one? So yep.
So you either pull it out of gear, step on the brake, or
Yeah, right. Yeah. Sometimes you have a brake underneath, so you have to like foot the brake, right? And then if you have an even smaller one, put into neutral. That's how you stop the machine. So before you operate, make sure, make sure where the stop machine. This is not only for race, but race sometimes it's hidden. That's why I'm kind of insisting. Because you use modern machine tool, right? So always you have a red button, but you don't know once you go out. School, of course, we provide safety one, right? But the real world, it's not unsafe. It's just old one, or modern. That's about it. But anyway, that's kind of hidden information, which is super important. And then this is another one, so I don't think we need to explain again. This is a little bit bigger one, right? And then if I can add one more thing, is chuck. You have 3 jaw, right? Usually, right? But there are four jaw, right? So then go like that, right? So then I'm not good at that. I can 4-1. Oh, it takes forever for me to, just. But 3 jaw, like I just mentioned, make sure, like dial indicator. And if you have to do precision machining, then you will use 4 jaw, or your workpiece is somehow square kind of end or something like that, right? But unless you, really need to use, if you are beginner, try to go 3 jaw. Okay? I just want to tell you, I just cannot. I just cannot. I gave up a long time ago, So, yeah, I think I machine a lot, but But anyway, I think this is older picture. So I want to share the modern one. That's on the video, right? I don't know. You check video. Did you check video? Did you watch? No, sorry, I have to go to so many. So now, even if I hide like that, but the screen, I don't have any, right? So let's see lecture, and then just like that, but I cannot do, for, right? Okay, then note, then this one, right? Okay, so let's, because this is very old. You may not use or you use, we don't know. So machine tool, there are many machine tool industry, but this is just one of the like website. They put a lot of video, So this one is fundamental, but if you learn more, and then just some of the example or the video, that's good. Just okay, because it's too many. I'm not trying to impress or anything, but I thought maybe you want to know some of the high-tech. Okay, one more. Okay, maybe shoulder. Sorry, I watch many, so I just which one is good, and I put shoulder, and I also put like surgical okay, let's go this one. 2 minutes. So this is like upscale, but machine tool, Impressive, right? Right. So this is not future. This is now. So if you are going to this world means not, you don't have to be like a machinist, but you will be engineer or researcher. But you have a capability to use. Use means that you can design some parts using this kind of machine tool, right? So this is turning and milling, the combined mill turn. So but anyway, this is not special. This is normal. Your standard. I didn't think about when I was your age, But anyway, like I said, like synchronized, that's impressive. And also look at this surface in the curvature, So that's, we are studying very fundamental because we have to understand to bring you to this level, right? Yeah, that's why. So some students may say like, oh, this is old. Yeah, but old, we need to understand. But I still want you to know this is standard for you, your generation. Okay, because otherwise once you go and then you just don't know, maybe you will be embarrassed, because people use it. Okay. Impressive, right? Just please, I feel like I'm the only one who is impressed by this, Right? Okay, so now, machine tool, right? Turning and then machine tool, right? So how about drilling? So drill press, did you use drill press at least one time? Did you make hole? Yes, good, good. So now you have some idea, right? So drill. So drilling is, actually 7.3. But if you make like more than M8, like 8 millimeter, don't do by hand, You let machine do, like big one. I mean, I get scared if that's kind of, that size, I don't know how about you, Okay, so drilling. So we will have a video, but I think, before we go that, I can share some, like PowerPoint, but also, figure. So that case, 717, 718, 719, and 720. So let's see. So 717, right? So that's this, on the screen. So it's a little bit smaller. So this is, the kind of, tool for drilling. So that's a simple one, right? Drilling, like twist drill. So you have two cutting edges, right? And then just rotate, right? And then you cut, and then this angle, So that's helix angle. So depends on what kind of material you machine, hard or soft, then how the chip flow, how you are going to eject. Because turning, you have a chip outside, right? Drilling, if you go in, you have to feed chip go out, right? So this angle, how many turn chip has to travel, that makes a difference. So that's why, it's changing. But for now, just want to use this one, and then we watch video, so you get a better idea. So this is a regular one, right? I mean, regular means like a twist drill or, just standard. And then probably, you will do maybe like a counter boring, like a counter bore, if you want to, you have, piece 1 to 2, you want to combine, right? So then, drawing-wise, okay, so this is section view, right? This is, right? And then top, if you have room, you can, like just make it like, just like a through hole, right? And then you can put, screw or something, right? And then you can just, tighten, right? But if you have no room to have this head, then you have to put this, inside, into one, right? So then you will make something like that, right? So that's, that's counter bore, right? You have to use. So that's the one I just mentioned, counter bore. Maybe you will see this line too, Yeah, but anyway. So then that's, counter bore, this one. So you can make like, So these are like probably, you normally, experience. But hole making, and then you will have like just regular through hole, right? But through hole, sometimes you are not going to have a smooth surface, not like the video we watch. Even video, so rough cut, I mean, video is outside, rough cut, and then you have some end mill or something, and then, go like final cut, right? So then same thing happened to, like drilling. So if you use drilling, then you have a hole, and then if you have to make a little bit bigger, boring, right? Bore like good. And then you will have reaming, right? So then reaming, you have fine surface. Fine surface means like a smoother. For example, if you have to put bearing inside, right? Bearing like outer, bearing, you have to put it. Then maybe you have to have a fine surface, right? Because otherwise, you may have some, debris or something, scratching. And then also dimensional accuracy, right? If you don't need to worry about just like a big hole, like this case, let's say like I just want to have put M4, just screw, and then maybe this part. So let's forget about the counter bore, like regular case, then go to like that, right? Maybe bigger. It's not symmetric. I apologize, but it should be symmetric, okay? But then you will have this hole. Maybe this is millimeter metric, okay? M4, M using. So then maybe you will have 4.5 or something a little bit bigger, right? But you don't need to worry about the surface like roughness or something, right? Then it's okay, right? Because you don't need it. But if it's a bearing side, that's a different story, right? So, then just maybe you do center punch. You don't do Sharpie. Center punch, like you scribe, right? And then center punch, and then you get the drill, right? And then you have like, just good, hole making, right? So if it's, it's just like a hole, that's okay. But then after that, boring. So this can little bit enlarge, right? Because you are going to additional machining and the precision, like kind of, circular geometry you want to have. Then you will do bore. And then reaming is the last one. So that back to figure 7.7 and 17. This is one way, one kind of reamer. So reaming is the action. Tool is reamer, right? Reamer, right? ER, no? So this, and then you will, depends on by hand or machine, no? You will make it. So if you don't need fine or like really accurate hole, you don't need to use reamer. You can just drill. Maybe drill, and then if it's like not so big hole, you can jump from drill to reamer. That's okay too. Maybe big one you want to have boring, but something. But the important part is this order. Drill comes first, second bore, third reamer. Okay, because bore means bore is not hole making. Bore is hole enlarging. Okay, you cannot just bore. You have to have always pilot hole, which means drilling comes first. Okay, don't forget this order. So anyway, drill, and then depends on the application, what kind of procedure you take. That's on you. And then more like detail, like this is terminology. You can probably go review by yourself. But like lake face, right? And then maybe important is like what cutting. This is a cutting edge, right? Here, like cutting edge. And then maybe other is like so. Then lake face because you cut. So whenever you have cut even drill, chip flow, that's lake face. So that's so once you understand this fundamental two-dimensional orthogonal cutting, you can transfer your knowledge to others. And then I think the others, margin red, and then fruit. Yeah, fruit is kind of helix angle, and fruit goes like chip goes like that. I feel like I'm dancing. I hope they don't record my action. So, but anyway, this 718 is for the like a terminology. So I want you to review, and then 720. So this is the kind of some other example. So this solid hole making, right? And then trepanning, and then next is counter boring here. I try to read. I should just take a picture. Counter boring. So something like that. And then reamer is going to be this is another EML6324, and then some sort of terminology. But Lima probably I don't know, DML, did you use Lima? Maybe not, just whole? Yeah, you do? Okay, yeah, so Lima. So then maybe you already learned, so I don't have to spend much of time, but just go review. So I think we can watch video, then maybe you can understand. Even if you forgot, once you watch video, I believe you remember that. So video, then okay, so basic hole making.
A drill is a round end cutting tool with one or more cutting edges and one or more straight or helical flutes. Drills with two edges and flutes are by far the most common. Drill types include helically fluted twist drills made of either high-speed steel or carbide, and indexable insert drills, which have steel bodies with one, two, or more carbide inserts. Carbide drills are stiffer than high-speed steel drills, so deflection is less, cutting speeds are faster, and holes are more accurate. Carbide drills are especially useful in hard or abrasive materials. Solid drills of high-speed steel or carbide dominate applications up to about a 5/8 inch or 20 millimeter diameter. Spade drills and indexable insert drills cover the larger size ranges. The twist drill is a roughing tool with two cutting lips. The three essential parts of the twist drill include the shank, the flutes, and the point. The shank is the means by which the drill is held and driven. Twist drill shanks may be straight, for use in collets, and keyed, or keyless type drill chucks. Shanks may also be tapered for mounting directly into machine spindles or sleeves which fit in spindles. Flutes let coolant into and carry chips out of the hole being produced. Both of these functions are essential for the drill point to continue cutting under the severe conditions of rotating at high speed in an enclosed space. The helix angle of a drill's flutes can vary dependent upon the material to be drilled. A standard helix angle of 25 to 33 degrees is optimal for steel and cast iron. A high helix or fast spiral angle of 35 to 40 degrees is used for low-strength materials like aluminum, and a low helix or slow spiral angle of 15 to 20 degrees is used for drilling brass and plastics. The drill point, which does the work of metal cutting, is formed by the two cutting lips and the chisel edge. Even though drilling is the most common metal cutting operation, the majority of drilling is not performed on drill presses or other dedicated drilling machines. Most hole making is accomplished using lathes, machining centers, high production transfer machines, or almost any machine capable of providing a relative rotation between the workpiece and cutting tool. The sensitive drill press is a low-powered drilling machine used for drilling one hole at a time in small workpieces with small diameter twist drills. The manual feed gives the operator the feel for the operation, which is why this machine is called the sensitive drill press. Although this drill press used to be a common device in most shops, it has now largely been replaced by the more versatile knee mill for most manual, low-volume hole-making operations. The radial drill is used for drilling in large workpieces. It has the flexibility to reach surfaces that cannot otherwise be reached easily. The arm, which moves up and down, carries an adjustable position drill head that can be raised, lowered, and pivoted around the column. Gang drilling machines consist of two or more drilling machines mounted on a common base or table. Often, these machines are operated sequentially, with each spindle carrying a different tool and workpieces moved from one spindle to the next. Self-feeding drilling units operate automatically for repetitive work once the stroke, speed, thrust, and feed have been set. They can be used for reaming, tapping, or other operations as well as drilling, and can be mounted singly or in groups. In mass production, most drilling is done with multi-spindle machines or drilling units with anywhere from 2 to 10 or more individual drill spindles. Rotary motion from a central source is transmitted to the multiple spindles. The layout, with the positions and distances set between the individual spindles, is designed to fit a specific part. NC drill and tap centers are like lightweight machining centers, dedicated to hole making rather than milling. The tool changer is usually equipped with 12 to 20 tools, allowing multiple operations to be performed on single or multiple holes.
Okay. So now, you get the idea, right? So then, like you see that hole, right? So then what kind of drill press or how much power required? You need to know, right? Because otherwise you try to machine and then maybe drill is going to be stuck. And then you break, right? I mean, I don't know if you did tapping, right? Have you ever experienced you break the tap? At least maybe, I don't blame you, I did too, So, right, but once you, like somehow mismanage, right? And then you cannot remove tap. But did you? Yeah. And then, if you have like only one piece, you have to have like weight if you have to rotate, right? And then you have to balance, right? You have to put something, right? So understanding how much power, your machine, drill press, in this case back to drill, we need to know how to estimate. So today I was hoping to cover the calculation, but I just want to draw, then because I don't have to draw next time. So once we draw, then we finish, and then we will move on. Move on means that we will have just close today's lecture. So let's draw together material removal. Material removal rate and force and torque. Force, torque, and power. Too many, but it's kind of set, So figure 7.23. I really recommend you to draw with me. That's why, because otherwise you watch video, you probably you understand, but if you draw with me, you understand more. That's good, So this is the drill, right? And then we put D, diameter. We rotate, we use N, rotation. And then you have, some material you are cutting somehow, cutting, like this is material, okay? Something like that, right? So then you have, you rotate and then you feed, okay? So you have cutter here, like you cut this material here. So this is half of the, diameter. This is 2, okay, half of, it doesn't look like 2. So it's, half of the diameter, and this is the chip area, right? And then this, we use FT. This is, feed per tooth, okay? And then force-wise, this is a dead center, right? So you have this. We see FC. We use, this is a central force. Okay, and then like chisel edge, and then you have Fn. This is like a normal force. And then you are rotating, right? Because it's drilling. So I cannot draw, but tangential direction. So we put like Fn, and then tangential direction you have Ft. Okay, so that's tangential force. Again, this is really like tangential direction, the cutting. direction. So Ft is the most important when we estimate power or like torque. So I think now we kind of draw. So using this drawing, we will continue then a simple estimation, the equation, the formula, and then we can do some exercise, and you get a better idea. Then we can move on to milling process. Any questions? It's good? Okay, thank you and have a good weekend. See you on Monday.